Hi, my name is Edward George Timoshenko. I was born in 1969 in the former Soviet Union. I became a student of the Department of Physics at Moscow Lomonosov State University in 1986, one of the top universities of the country, which I've graduated with honors in 1992, soon after the collapse of the Soviet Union. Then I was briefly a PhD student there, and I received my doctoral PhD degree in 1995 in theoretical physics. After which I've moved to Ireland, where I was offered my first fellowship as a postdoctoral student, and then I became a lecturer at the School of Chemistry of University College Dublin, UCD. And I've been working there since, despite visiting various other universities in Europe, United States, and Russia with my lectures and for scientific collaboration. Recently, I took an early retirement for health reasons, and I'm continuing my work, writing books, and do my private research, among other interests, which I'm pursuing. So today I would like to introduce you to a series called Concise Lecture Notes in Physical Chemistry. It has 5 books published by Amazon in electronic form as Kindle books, also in printed version, which you can order also from the site. All the links are available in the description to this video. So they are broadly based on my teaching experience, mainly in the Faculty of Science of UCD, among others. The course is designed for equally chemistry and physics and theoretical physicists and various other similar or related disciplines of science, condensed matter, molecular simulations, computer modeling. So I'm a theoretical physicist who was seriously using computer-aided design. First I worked in nuclear physics and particle physics, then I moved to molecular physics and physics of polymers and biomolecules. So the first of these is to do with quantum mechanics, also statistical mechanics. They're absolutely indispensable for theoretical understanding of these complex subjects, and so I'll go through each of the books. Basically, this course covers the main subjects which I was practically lecturing on, and is presented in a very concise and self-contained manner with only basic mathematical prerequisites necessary for their study. All the results are presented and derived from the minimal first principles and lead directly to the most important results, which are widely used in physics and chemistry. So my lecture notes don't have much description. They have many equations, many graphs, and they're very easy to follow and ideal for preparation for the exams, and all are very compact, and apart from presenting the derivation of the main equations and explaining the principles, they lead directly to the useful results. Illustrations I prepared myself, mostly with help sometimes from my former students, and so I'm going through 5 of these books, which I hope you could enjoy and they find useful for your preparation for exams, also if you want to study these subjects independently. I hope to do maybe translation from English in the future to other languages. So the first book is on quantum mechanics. They're all very short and concise, as I said. So quantum mechanics is the core fundamental foundation for understanding the periodic table of the elements, chemical bonding, shapes of molecules, and chemical reactions. Along with the minimal background on the relativity theory and the theory of electromagnetic fields, which are presented here. It forms the basis of most of physical chemistry techniques which are used in real life. These are, for example, spectroscopy, X-ray crystallography, light and neutron scattering, nuclear magnetic resonance, chromatography, electrochemistry. Also, there are applications in the fields of atmospheric and solutions chemistry, studies of polymers, liquid crystals, as well as of biologically important molecules such as proteins, nucleic acids, DNA, RNA, viruses, and biochemistry, to mention just a few. So it's a very broad scope which these books are useful for understanding and further studying. Very briefly, so the first book deals with quantum mechanics. It was presented as a 12 lectures course, so I just list the main topics very briefly. So we start with problems of classical mechanics. We look at Planck's and Einstein's ideas. Then we revisit classical mechanics based on the Newtonian equations, and we introduce Poisson brackets and Hamilton and Liouville equations and give various examples. Then we proceed to observables and states, concepts, and then we discuss particle-wave duality in quantum mechanics, de Broglie equation quantization, superposition principle, and give the probabilistic interpretation of quantum mechanics. We discuss eigenvalues and eigenfunctions, Hamiltonian operators and other observables, stationary states, and transition probabilities. We look at time evolution and introduce the main equations of quantum mechanics, Heisenberg and Schrödinger equations, which lead, of course, to the famous Heisenberg's uncertainty principle, and we discuss the wave functions, translational motions, continuous spectrum and bound states, particle in a box and behind finite wall, look at tunneling, and look at various other examples of systems. Then we naturally proceed to vibrational motion. So we describe harmonic oscillator in one dimension. We look at the normal modes for coupled harmonic oscillators, which describe molecules and chemical bonds. We introduce normal modes and the center of mass separation. We look at three-dimensional systems. We separate variables. We introduce angular momentum, a look at rotational motion. Then we proceed, of course, to the hydrogen spectrum, hydrogen atom with a Coulombic potential, and also introduce the concept novel to us, which is known as spin, and introduce Pauli principle. Finally, in this course, I introduce Born-Oppenheimer approximation to describe other types of atoms. We look at how the periodic table electronic configurations are formed, atomic and molecular orbitals, and bonding, and how it's explained with hybridization and Schrödinger equation. So this is only a preliminary course in quantum mechanics, and obviously one has to study more seriously quantum chemistry, which is a separate course. That's the first book. The second book is Statistical Mechanics and Thermodynamics. Both of these were presented in the third honors course in chemistry, for example. So after a brief introduction of the probability theory, we look at the main principles of statistical mechanics. These are systematically developed from the first principles of the equilibrium theory. So in this course, I'm only discussing the equilibrium theory, but apart from statistical mechanics, we describe also thermodynamics and how they are interconnected with each other. So the course proceeds from a mechanistic description of molecular and atomic motion for macroscopically large physical chemical systems. We introduce the concepts of thermodynamical ensembles. For an isolated system described by the microcanonical ensemble, the laws of thermodynamics are derived from the first principles and the principle of a priori equal probabilities of microstates in the thermodynamic limit. The concepts of the entropy, temperature, heat capacity are defined and introduced. We proceed to systems in a heat bath and obtain the Gibbs canonical distribution and explain the concepts of the partition function and the free energy. Then we derive the ideal gas law, which is obtained, as well as corrections to the ideal law, leading to the van der Waals equation of state, very important equation in physical chemistry. We look at vibrational, rotational, and electronic partition functions for molecular systems. We define the concepts and introduce of open thermodynamic systems under fixed pressure and the associated grand canonical Gibbs ensemble, along as the concepts of chemical potentials and enthalpy. And finally, we look at quantum systems and describe two types of statistics, which are Bose-Einstein and Fermi statistics. And that is the second course called Statistical Mechanics and Thermodynamics. Next course is about computer modeling, because most of these equations are too complicated to solve on a piece of paper, and we use modern computers and supercomputer facilities and cloud computations to do this. They very heavily rely on ordinary mechanics, statistical mechanics, and quantum theory. So this is a course on computational chemistry and computer simulation techniques. We describe the importance of these in silico methods in modern chemistry and physics of complex systems, and these are increasingly heavily used even for modeling actual cells and interactions with viruses and for drug design and so on by major pharmaceutical companies in the world. So it's a very serious applied part of science. We introduce the main underlying concepts and overview the major techniques used in this very broad field of research. The concepts of idealized computer and virtual computer-based experiments are explained. Further, we discuss various popular computational packages which are used in the world. We return to Born-Oppenheimer approximation for electronic configurations. We look at classical treatment of the motion of nuclei and potential energy surfaces, force fields, and geometry optimization and energy minimization methods, which are discussed in a great deal of detail. The Newton's equations of motion and their numerical integration methods are presented. Numerical solution of ordinary differential equations in general is outlined first. We look at examples of chemical reactions and molecular dynamics in details. We study simple examples of damped harmonic oscillator and the phase space of this system. We consider the Euler and Verlet algorithms, concepts of thermodynamic ensembles from statistical mechanics and incorporated into our description. And we perform calculations and give examples for various systems, for observables and their averages, how they can be sampled and computed. We look at molecular dynamics techniques in NVE, NVT, and NPT ensembles at fixed various external conditions. We discuss the importance of the boundary conditions and cutoffs, which simplify our calculations, make them feasible for really complex systems. We do calculations of examples of very important observables and we look how the system approach the equilibrium state. And we look specifically at simulations of gas, liquid, and solid states, as well as of phase transitions which occur between them. Next, we proceed proceed to the description of molecular solutions, because most of the biological process and chemical reactions occur in solutions, not just as in a gas phase for chemical reactions, for example. These have specific techniques associated with how we treat the solvent separately from the solute molecules. For this, we introduce Brownian, also known as stochastic dynamics, based on the Langevin equation, and the use of random numbers generators is considered in detail because randomness is part of these systems. We progress towards the equilibrium simulations naturally and introduce a very important technique known as Monte Carlo importance sampling methods generally, and the Metropolis algorithm specifically, after the name of scientists who suggested it. Finally, we look at the methods for solving Schrödinger equation in general. And for instance, we consider variational approach and different applications of these to real systems. And we review generally modern quantum chemistry. In this very short course, we just give a brief introduction to a vast field for which various Nobel Prizes were awarded. I have to say there are many Nobel laureates I mentioned in these courses. These are the foundations of modern science, which are necessary for understanding both physics, chemistry, and biology in the modern world. Now I proceed to more advanced courses, which were presented in the fourth year honors degree course, and also for postgraduate students as well. So next book is called Statistical Mechanics of Phase Transitions and Kinetics. So it goes beyond the equilibrium theory, which I've described before, and so it deals with more important practical examples. So we give a brief overview of the equilibrium statistical mechanics first, which we've described beforehand. We recap the ideal gas law. Then we look in more details to the corrections of the ideal gas law and the van der Waals equation of state. We consider the coexistence of two phases, the Maxwell rule, the Flory-Huggins theory of polymer solutions is derived. We look generally at phase transitions and phase diagrams for various systems and describe not just domain but also metastable states which can exist for a limited time. We look at applications to chemical reactions, chemical equilibrium in solutions. We derive the Dalton, Raoult, Henry, and Van Hoff's law. All are very important in solution physical chemistry. And then we describe briefly the approaches towards the more important and more complicated subject of non-equilibrium statistical mechanics and kinetics of phase transitions, how they occur in actual time. So then finally there is a more complicated course which describes a different approach to quantum mechanics. So far I've only mentioned two formulations of quantum mechanics based on the matrices or operators due to Werner Heisenberg and the wave mechanics due to Erwin Schrödinger. And both of these were reconciled by another Nobel laureate, Paul Dirac. But there is another formulation due to another Nobel laureate, Richard Feynman, which combines and explains, gives an alternative, if you like, formulation of quantum mechanics, and it proves most promising for more complicated systems, and especially if we go from molecules to quantum chemistry to actually understanding complex molecules, as well as studying particle physics, such as experiments being done in CERN, described by the so-called standard model of four forces of the interactions of nature, which is beyond our course, but the same techniques and the same underlying ideas are used there. And this is known as the path integral approach to quantum mechanics. And this course was initially presented by my PhD supervisor, late Professor Nikita Sveshnikov at Moscow State University. Then I worked on this subject for my PhD degree and for my research, and I gave my version of it as postgraduate courses at various universities and as advanced undergraduate. So again, it doesn't require any additional mathematical input, but it's more complicated and has more equations and fewer graphs in this last book, which I consider probably the most important of the 5 if you reach the level. So you must read them sequentially or separately, whichever is you prefer, but to understand path integrals you have to first study a book on quantum mechanics, which gives you all the preliminary information. So this book is based on the first principles of quantum mechanics, and we derive the path integral representation for the evolution, amplitude, the partition function, and other observable averages, which I've mentioned in previous books. We compare different schemes of quantization yielding corresponding symbols of operators in the phase space. So the same language as used in statistical mechanics and quantum mechanics is used here as well. Surprisingly, a nice approach. Now, briefly, the overview of the course. By the way, it requires nothing more than calculation of Gaussian integrals. So it's very simple, although it deals with more complicated issues and techniques, more advanced techniques. After a brief introduction, I'll look at the mathematical basics. So all the mathematical basics are given in the book. We look at symbols of operators. We return to Hamiltonian formulation of classical mechanics, quantization of operator and operator realization of quantum mechanics in Heisenberg's picture. Then we look at ordering of operators in the quantization procedure. We look briefly at the Hilbert structure and the translational operator, which move things in space. We consider specific examples of symbols of operators known as Weyl, normal, and anti-normal symbols. Then we return to our favorite system, which is harmonic oscillator. We look at the associated harmonic oscillator symbols, quantum mechanics of operator symbols, and we make natural connection to classical mechanics. Then we look at exponents of operators. We define the normal symbols of the evolution of operator and calculate it. Weyl symbol of the evolution operator, and finally we derive the famous equation due to Richard Feynman, which is the path integral for the Weyl symbol of the evolution operator. So that is the outline of this self-contained course. It's very brief, a bit dense at some places, and very easy to follow, and you don't need any further inputs for its study, but there are various references presented therein and plenty of graphs and supplementary material available. I wish you success in your studies of science and enjoy my textbooks. Thank you for your attention.